Good afternoon, everyone. Myself, Vaibhav from Dr. Vaibhav. I recently graduated with a PhD from Dr. Today I'm talking about a plan B for gigascale carbon sequestration, which is CO2 hydrates based carbon sequestration on the seabed from the University of Texas. So the outline for today's talk is essentially first I'll start with an overview as to why we need CCS in general, which is carbon capture and sequestration, and then how CO2 hydrates can act as an option for CCS on seabed. Then I'll talk about briefly talk about comparison between CCS and the traditional carbon storage technologies, such as mineralization. And then I'll talk some ongoing efforts at Bahadur lab on this level. And then finally I'll conclude with some conclusions and findings. We talk more about this later. To give a brief idea, this is a video of hydrate formation in water contact. This foamy structure you see is hydrate. So give an overview, why do we need CCS? So if you look at this graph here, the black line is the CO2 concentration in the atmosphere in the last few decades, and the red dots are the temperature around it. So you can see there's a red plane between the two, which means that the temperature increase that we have seen after the initial revolution is essentially the cause of this excess CO2 in the atmosphere and therefore anthropogenic or cosmic use. So we to compensate for this excess CO2 in the atmosphere, the target set by Paris Agreement is 10 gigaton per year by removal of CO2 by 2050. Right now, we are at 50 megatons per year, so we're 3 orders of magnitude this year. So therefore, we need more and more carbon capture and sequestration of emissions. Now, why hydrates for CCS? So to give a brief idea of what hydrates are these ice-like structures which are formed with water and the gas molecule. The waters are bonded together with hydrogen bonds, and the gas molecule and the CO2 methane. Today we're talking about CO2 hydrates. These are dense, solid, and immobile, and compact forms of CO2 storage. These are distilled water, so they're naturally reduced. Now, if you look at this graph here, the green curve is the temperature pressure curve from the sea surface. So here's the beach. Go deeper, the pressure increases, temperature increases. Once you hit the seabed, your temperature increases and pressure also increases. Now, if you overlay the blue line, which is the CO2 hydrate equilibrium curve, you get ABC region where hydrates are completely stable. And we are wishing that hydrates best form would be best deployed would be on the seabed. Otherwise, again, under seabed, we have some issues. And the good thing about this approach is that there already has been pre-existing gas hydrates in these regions for thousands of years, like methane hydrates and other hydrates. So we believe that this is the right for carbon sequestration. Overall, we think that CCS is insurance for the planet, so we need multiple scalable options. Now, how do we approach this seabed sequestration of hydrates, right? We are essentially proposing a four-step approach, and currently we are focused on the first step. The approach being first to form hydrates slurry on the land, then we transport the slurry to the seabed. We compact said slurry into a plug, which looks like this. This is a plug we made in the lab. Then we seal this plug with an artificial sealing and dispose and monitor on the seabed. So overall, this is supposed to on the seabed in a compact and steel form. And currently we're focused on fast formations hydrates on the land. To give a comparison of CO2 hydrates on seabed versus traditional sequestration methods, the more established ones do insulation and CO2 mineralization is also an alternative. Overall, our technology requires less area footprint for monitoring. You could make more than 100 square kilometers for a reputation project, but compact hydrate storage seabed fills is what we're calling these lands in these sites will only need a square kilometer for. Another thing to note is that the hydrates dissociate very slowly, so there's a lesser possibility of leakage and very less detrimental leakage, and easily fixable. Another thing to note is that ocean is available everywhere, so availability of the suitable site is more for hydrate storage than geological condition. And lastly, and most importantly, is that for geological condition, we need like higher purity solutions, more than 95%. But for hydrates, because it is also said to look at as a means for carbon capture, you can work with like 50-60% purity. So this drastically reduces overall CCS costs because we know that carbon capture cost is a major component of overall. To know some key challenges, is that hydrate formation is known to be very stochastic and slow. So what we are currently targeting is that main problem. So with the aim that we want to develop a chemical-free, inexpensive, and fast hydrate slurry on foam formation. To start with, nucleation, we saw that metals seems to increase hydrate nucleation significantly. And to name two, aluminum and magnesium process. Even among those, magnesium alloys work the best. And we are seeing that in a quiescent medium with no other chemicals, with magnesium alloys, you can get nucleation within 3 minutes, which is very fast. So essentially, on-time hydrate nucleation. This video shows hydrate nucleation from the surface of the magnesium plate and the interface of gas water, and essentially it spreads around the interface. And then there is no more contact between the gas and the water, so it's very slow to that. Eventually, over time, it becomes. And you know that now that the nucleation problem is solved because magnesium alloys seems to do it on demand, we move on to growth. For growth, we develop a system setup where essentially we're constantly flowing gas in and out of the power reactor. And with a flow controller to measure the flow rate and then back to schedule to maintain pressures. To give an overview of the exploded procedure, essentially we start with the ignition plate either inside the plate system or with a magnet-based mechanism that's in the overhead space. So you can just drop the plate into the hydration. And we see that bubbles come from the bottom of the space. If hydrates form on the interface and fresh bubbles essentially push this hydrated foam upwards and add on to that foam, and eventually it becomes like this. So after like 3 minutes, or depending on the pressure, 1 to 3 minutes, 5 minutes, you get a whole foam of hydrate. We believe that the constant inflow and outflow of gas bubbles and the constant continuous renewal of this gas water interface is what is improving this growth significantly. To measure this growth rate, we coined this sequestration rate term, which is usually the mass of CO2 inside this hydrate form, and divided by the time that hydrate formation was occurring, volume of the reactor for scalability purposes, and then a pressure supporting term for operational condition purposes. This is the reactor pressure that the system is running at, this is the equivalent pressure at the reactor temperature is running at. Another term we noted is the conversion efficiency, which is mass of CO2 inside the form divided by the total mass satisfied with the system with kind information. Given an idea of procedure for experiments, we essentially stabilize the pressure and temperature of the system, and then we drop ignition plate and we observe near instantaneous information for ignition at higher pressure. So here you will see ignition plate drop. There we go. And pretty much right after the hydrates start to form. And this video is not set up, this is real time. So this shows how quickly we are able to form hydrates, and we can convert that CO2 into these crystallized structures or solidification. These are all the results all the key results of the experiments that we did. To give an idea, overall we're seeing that if the pressure is higher, you get a sequestration rate of around 1200. When the pressure is lower, you get around 200, which is 500 kSh. Now, if you were to use salt water instead of clear water, which would be beneficial because then you can just extract it from the ocean, then you get a 20% reduction in sequestration, which is not that bad for the purposes of not having a desalination. And then, if you look at these numbers and you scale them with volume for, let's say, 5 vessels of 10 liter cubic reactor, you get about 1 million per year sewage, which is the size of an industrial ship. And another thing to note is that this sequestration rate is greater than 6 times the fastest that we have seen in the literature for hydrate formation. And and the reason for that is continuous interface reading with the internal flow. We did a parametric analysis of pressure and initial mountain flow rates in time for head formation. We see that the more you wait for head formation, the rate increases, which is expected because head formation is a thermal reaction. The increasing in the flow rate increases your overall sequestration rate, but not nearly by the margin that the pressure is. And magnesium increase only barely increases the sequestration rate. So the overall we say that magnesium is an essential catalyst for head formation, but it is more sensitive to operating energy, the growth rate itself. Moving on to techno-economics. For this plan, we are currently focused on the first half of this overall pitch for the techno-economic model. And to mimic that, this is what we're trying to include in our model, which is essentially a gas supply and water supply at specific conditions. We have gas recirculation system, and we have a separate gas splitter for pre-dissolution of the water, so that you can increase the overall sequestration with the pre-release of water. And for this analysis, we have excluded the extraction methods for hydrate from the CR. And we essentially use one reactor first to understand the economics, and then we add on to it. We will see why. And we choose one pressure temperature condition and the fixed height and diameter and the conversion cost. The overall motivation is to develop a techno-economic model framework that can be covered with some results, and you can optimize this techno-economics. So if you look at the cost contributions in our own reactor, you see that for one reactor, 1 million per year project for 30 years, we are looking at around 700 megawatt hour per day, which is about 50% of our total cost. And the emission investment cost is about 400 per year, is about $150 million. And among these, the cooling energy needed for external formation, which is green power, and the compression power, which is blue power, are primary contributors to overall energy demand. Refrigeration and compression, again, the green and blue, are primary contributors to energy capex. And the bubble column reactor and the gas recirculation system, so which is these tiny sliver in these two, have very negligible costs. So this is that you can just have more and more reactors and have more and more recirculation and not worry about having a high conversion factor. And you can get a good scale at a good scale of project at minimum initial costs. Therefore, we increase the number of reactors in our model, and we suggest that let's say 10 reactors are operating with 3 meter diameter and aspect ratio is the same as the last reactor, and these are operating in parallel. And here the motivation is to extend that original model to accommodate for multiple reactors and also to the influence of the conditions. The gas and flow rate, water and flow rate, etc. were scaled in that with the reactor model. So first we just start by maximizing the driving force, which is essentially the pressure and the temperature. We push as much as we can, limit the liquid CO2 formation, because we know that if liquid CO2 is formed, the hydrate formation rate is expected to slow down. So we push the pressure temperature as much as we can while avoiding liquid CO2 formation. So we do that for 3 temperatures, the pressures on the 3 are also changing. We see that the overall scale of the project, which is this green curve here, is maximized as the quantity. So the optimal PT is for these cases is 524 kShg and 130 kShg. Another thing to note is that in these conditions, as you can see, the blue green curve is ranging from 5 to 10, which is about twice as much. But the blue curve, which is the cost per ton, is only changing from 22.5 to 21.5, which is very different, less than 10%. And this is like almost 2 times. So the cost per ton does not change as much with the changing operating conditions, but the scale of the project significantly increases. And we also learned that the system is operating best close to liquid CO2 formation conditions while avoiding liquid CO2 formation conditions. So therefore, essentially maximizing the benefits. Next is the difference of operating temperature. So for these, we kept the pressure fixed at 3 megapascal for 4 kShg. And we increase the temperature from -5 all the way to 3. And you see that if you're going below -1, you're just getting ice formation and in salt water. And because you're getting ice formation, you have less water available for hydrates, so you slow down the curve. So you get a maximum on the scale of the sequestration. And this reason for that is the ice formation and the reducing the effect of increased cooling at lower temperatures. So for this pressure, the maximum best temperature was -1. To conclude today's talk, overall we think that benefits of our technology over reservoir injection to the lower probability of leakage. That includes cheaper monitoring. It has a potential reduction of overall CCS cost by accepting lower purity CO2 streams. Another thing to note on this point is that we have talked to some dedicated capital folks, and they seem to say that going as far as CO2 is going from air purity to 40-50% purity is about the same cost as going from 40-50 to 97 plus, which is what the sequestration maps. So we can reduce the TAC costs by or reduce costs by half by implementing the technology. And then we see that the sequestration rate of 1.2 kg per hour per liter of capacity is reported, which is greater than 6 times the maximum ever reported in the region. And this is because an open flow reactor with a constant gas flow at high flow rates, essentially gas is coming in and out, and the interface is constantly getting renewed, is the primary reason. And the magnesium is acting as a catalyst to enable that. And both of these together is what is causing this excessively faster sequestration. The hydrates-based CO2 sequestration can be accomplished by DI water, tap water, salt water, and ocean water. When we go from DI water to salt water, we reduce sequestration by about 20%. Do the same when we go from salt water to ocean water. Reason being, additional salts reduces overall emissions. And you also see that for a 1 million per year plant and a 30-year life, the total cost of foam production is about $36 per ton. But when we include multiple reactors, we increase the scale, we reduce the pressure-based conditions, we see the optimum changes to a scale of 9 million per year with the cost of $21. We were able to do that because the cost of the reactor itself and the separation costs are minimal, so we could add more reactors on the additional costs while increasing scale. Finally, I would like to acknowledge the lab members, the advisor, and the funding resources.
We have time for a couple of questions. Hi, this is Tom. So I read recently about the whole CO2 lakes concept, or essentially just pure liquid CO2. And how would you say that compares in terms of long-term stability, potential benefits, costs to hydrates? It's essentially the same thing, but instead of having hydrates, it's just a liquid layer of CO2 under water, like a basin, very deep.
Yeah. So the first 2 ways we are essentially solving that whole leakage issue with making hydrates. First being that is happening because CO2 is in liquid form, so it's moving. So it can very easily seep into cracks wherever it seeps. But when it's in hydrate form, it's solid. So it's not going to move. So first that part is clear up. Second is that the monitoring itself, when it comes to liquid CO2 under the surface, you need to do seismic. There's a lot more monitoring costs involved when you want to track liquid CO2 under the surface and to put liquid CO2 under the surface, especially because it's very deep in the surface. Here it's on the seabed, and we're expecting to have those seabed fills, which we call them, which is like essentially trying to treat CO2 as trash. So we have landfills for trash, we want to have seabed fills for CO2. And once we have those, they should be at a place where there's natural sedimentation. So over time, it will be more and more and easier to track because there are already optical fibers which helps you track concentrations on the sea surface. That's how we get into it. So there's many easier ways to track when it's on the seabed compared to under the reservoir.
Yeah, hi, thanks. This is interesting. So I'm just trying to understand the magnesium as a catalyst. So maybe it should be getting oxidized, right? In doing redox chemistry at a magnesium normally has an acidic surface, but if you're somehow disrupting that, you're oxidizing magnesium metals, magnesium ions, and creating some reduction products. So can you help me understand? In your foam cost is the mag cost, and that assumes that it lasts 30 years, and have you assessed sort of the lifetime of these metal surfaces?
So, as far as the chemistry behind why emission is promoted, we have seen emission carbons on the surface after it's done, they have to be taken out. We also have tried to measure the difference in the weight of the plate we use, and that is like the plate is sitting in the reactor with all those hydrates for like multiple days. And in the waste, we cannot even change the change. That's within the air margin. So the consumption of emission is in this.
But if it's precipitating on the surface, then it's not gonna.
It doesn't, yeah, it doesn't dissipate. That's what we see.
No, but
We see that-
you're still consuming magnesium metal to convert it to magnesium.
Yeah, so when we are doing this cost analysis, we neglected the cost of emission that's provided for the catalyst, for the action to begin. And the reason we took for that was because at least in our lab scales, we could not even measure the change of the consumption of emission for the action. And the science behind the chemistry and why it's promoting inflation, we're still figuring it out. We have tried to do a CIR, we have one or two hypotheses, but they're not complete enough to say for sure yet as to why is it magnesium so helpful with the mitigation process.
Thank you, Dan. So, anyone who needs to- We'll now have Kevin Van Veen, talk about electrification of steam cracking as a pathway to reduce the impact of the petrochemical industry on climate change.